Okay, so last time we met, gave you guys some problems on figuring out what network we're a part of, what's the broadcast, first usable, last usable, all that good stuff. So I want to go over do that. Sorry about that. So I want to go over another example here, see where you guys are at with it, and then maybe we'll talk a little bit about IPv6 again. Okay, before we do any type of binary or subnetting or anything like that, we always want to draw up our chart. So we draw up 8 bits. Those are just represented by ones. So I got my 8 bits up here. We use 8 bits because there's 8 bits in an octet of an IP address. That's why it's called an octet, hence 8 bits. And then I start with 1 along the right-hand side, and I double as I go to the left. Honestly, usually when students get something wrong on a quiz or subnetting, it's because they did their chart wrong. If you got that chart, you can usually do all your conversions and everything you need. So memorize that chart, how it looks, how to create it, and I'm pretty confident you should be able to figure out anything you would need. So here we go. Let's pretend I give you the 192.168.1. Let's go with the 202 address. And it has a /28 for an IP address. And what I want to know is what network is that device a part of, what's the broadcast for that network that it's a part of, and what other addresses are you going to find within that network. So what's the first usable and the last usable, essentially. So what we said yesterday is the first thing that you need to do is take your IP address and your subnet mask and convert it into binary, right? So here's my IP address in binary. So for 192, I need the 128 and the 64. And then the rest are going to be zeros. For a 168, I need the 128 and the 32, which gets me to 160. And the 8, which gets me to 168. I don't need the 4, I don't need the 2, I don't need the 1. For 1, that's an easy one. 1, 2, 3, 4, 5, 6, 7, 8. And then for a 202, why did I pick a hard one? 128 and 64 is 192. And the 8 is 200. And then the 2 is 202. Okay, so I got my IP address in binary. First step for figuring out any types of questions you'd ever get like that. Questions on this. Okay, then I take my subnet mask /28. That just simply tells me how many ones I have in my IP address, and I put it right below this. So /28 says I have 28 ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, and then the rest are zeros. Okay, then what I said is you go and you find where your subnet mask changes from ones to zeros, and that's right here at the 28th bit. And what you do is you draw your line. Okay? Questions so far? Okay, then there's 3 ways that you can use to figure out the network that you are a part of. And the first way I said is just to take what's on the left-hand side of this line and convert it back into decimal. And that's going to tell me the network. The second way I told you is to AND these together. And that's where you go, a 1 and a 1 is a 1. A 1 and a 1 is a 1. Anything ANDed with a 0 is a 0. 0 and a 1 is 0. 0 and a 1 is 0. If I had a 0 and a 0, that's a 0 as well. So you can go along the line and AND it out, convert it back into decimal, and that would work for you as well. The third option is to take this right-hand side and make it all zeros. Put this in blue. And then convert what I'm putting in blue here back into decimal. And this probably is the method we should be using, because what we said is when we have the right-hand side all zeros, that's our network. When we have the right-hand side all ones, that's a broadcast, and any other bit combination happens to be a client. So I got this drawn out. I'm going to convert it back. That's going to give me the network I'm a part of. So this number converted back is 192. This number converted back is 168. This number converted back here is just 1. And then I have 11000000. That is 192. So the network that the PC with an IP address of 192.168.1.202 is a part of is the 192.168.1.192 network. The subnet mask, well, I gave that to you. It's a /28, which is the same as a 22255.240. You converted that number back. I said I also want to know what the broadcast is, and again, a broadcast is when we want to reach every single device on this network. We said broadcasts happen with like DHCP traffic and HARP requests. When I want to send to everybody on the network, that is the broadcast. To figure out the broadcast, you take the right-hand side of the line and you convert it to ones. Green with this. So now I take the number here that's in green and I convert that back to get my broadcast. And I have 192, 168, 1 dot. This is a 192 plus an 8 plus a 4 plus a 2 plus a 1. It's 192 plus 15, which is going to take me to 207. So my broadcast, if I want to send to all devices on the network, I would send to the address of 192, 168, 1 dot, 207. Questions there? Okay, then we needed to figure out, well, what's the first usable address in this network? What's the last usable? Well, I can't assign. I cannot assign a device or a host on the network that address because that's the network. That denotes what network I am. Am I BSC's network? Am I the home network? Am I Yahoo's network? Whose network I am? That defines that network. So the first usable is one more than that. I can assign a device on the network the .193 to begin. And then the last usable, I cannot assign this. This is the broadcast. So it's one less than that. .206. So on my 192.168.1.192 network, I would see devices between 193 and 206. So 193, 194, 195, 196, 197, and so on would all be part of this network. And they would all have the same subnet mask, and they would all have the same broadcast. They're part of the same network, so they have those same communications. Questions there at all? Should I do another quick one? Yes. That's the spirit. That's what I like to hear. This is how I used to impress girls in college. You know that, right? Go out on dates, and I'd whip out some binary and show them how to do this, and they were so impressed. No, it's pretty boring stuff. I realize that, but the reason why we need to learn this is it's going to help with our subnetting going forward. But this is what our devices do all the time. Our devices don't know a decimal number; they know binary signals, on and off, ones and zeros. Every time a router gets a packet, it ands or figures out what network is this on. Where do I deliver to? What device do I deliver to once I'm on that network? This is happening all the time. They can do it much quicker than we can. Okay, so let's take let's do one of the BFC networks here. 165, 234, 48.132 with a /26. Real life scenario. About 10 minutes ago, I got an email from the BSC administrator. She said, hey, there's this computer, 165.234.48.132 on the network with a /26. It's handing out addresses. Do you know where it's located? So the first thing we need to figure out was what network is it on? Is it on the network in this room or the next room or over in the server room? So we actually just did this. So our first step is to convert this and the subnet mask into binary. So 165 in binary, I need the 128 and the 32, which gets me to 160. I don't need the 16, I don't need the 8, I need the 4, which gets me to 164, and then the 1, which gets me to 165. Again, if you aren't sure how to do this conversion, talk with Clyde or myself. We can help you through. You can also take out the Windows calculator, programmer mode, type that in, it will tell you what it is in binary. 234 in binary, I need the 128 and the 64 and the 32, which gets me to 224. I don't need the 16. I need the 8, which gets me to 232. And then the 2, which gets me to 234. And then the 48, and I realize I'm kind of going through these fast, but we don't have a ton of time. Good catch, guys. What is it? October? First mistake of the year. Not bad. November, even better. So where do I messed up with 234? Let me
yeah, right. You just
added one at the end.
No, it was an extra between. There you go.
There we go. Thanks, guys. And 48, I need the 32 and the 16, right? And then 132, I need the 128 and the 4. Okay? Then I would take my /26 and I would convert that into binary as well. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Okay, then what I do is I figure out where my subnet mask changes from 1s to 0s, and I draw my line. So where am I going to draw my line? Right here at this 26th bit. Now I know everything to the left. If I convert that back, that is going to be my network. So let me just do that, convert that back. That's 165. Convert this back. That's 234. This number here is 48. And then this number here, because I have just the 1, so it's 128. And really what I probably should do is make this a 0, because we said when we have all zeros on the right-hand side, when a device sees that, when they go through this process, they know, okay, that's the network address. So the 165.234.48.132 PC happens to be on this network. The 165.234.48.128 network. That happens to be the network in our little server room. Okay. Now I also want to figure out what is the broadcast for that network. This is a DHCP server we're trying to track down, and it was broadcasting out DHCP addresses. So I want to figure out what that broadcast address is. In order to do that, what we said, you make your right-hand side all ones. Hopefully what you're noticing is that subnet mask never changes, right? It's just sitting there. We're only messing with that top line. So for the broadcast, I make this right-hand side all ones. Convert this number back that I'm putting in blue decimal. And that's going to give me the broadcast. So I have a 165.234.48 dot. This number here is 163. Sounds good to me. So 165.234.48.163, that's an address we could use to broadcast out to everybody. We also said yesterday, there's also something known as the limited broadcast. And this is actually the address that DHCP uses. So we could either see this as a broadcast for this particular network, or we could see this address, which is a broadcast for all networks. Okay, I want to figure out first usable address and last usable address so I know what is within this network. So my first usable address would be 128. No, I can't use that, right, because that's the network. So 129. So 129. And then the last usable, I can't use the 163. That's the broadcast. That's the end of the range. So 162. So 129 through 162 is my range. I could take a device, give it any address on it here, like the 150, and it's going to be on the same network as this one. I could give it the 160, same network as this one. The 135, it's on the same network as this one. It could communicate. It would have the same subnet mask. It would have the same network ID, same broadcast. So what it really boils down to is just taking your number, converting it to binary, and then drawing your line. You draw your line where your subnet mask changes from ones to zeros. Then from there you can figure out by tweaking the bits on the right-hand side. Questions?
So this is a Class C.
Actually, yeah, what they actually did is they took a Class B here and they tweaked the subnet mask to make it into a Class C.
Okay.
Yep. Class B typically has a /16, but they did something called variable length subnet masking, which you guys will learn about. Also known as CIDR, where you can, CIDR basically is classless domain routing, where you can take any class of address and make it whatever you want. And that's one of the ways we've been kind of able to hang on to IP version 4. Questions? Okay, I'm going to look at IPv6 then. Okay, so yesterday we started a little bit with IPv6, and the first thing we did was take a look at it in terms of. Pull back up here, I lost it for a sec. We took a look at it in terms of why we needed it. We essentially said here that our IP version 4 addresses are becoming extinct or exhausted. I probably should say not extinct, because they're still around. But they're becoming exhausted, which means we've given them all out. We don't have any left. With IP version 4, we said there was about 4.5 billion addresses. Well, we concluded yesterday that there's about 8 billion people in the world. People have multiple devices, so we quickly ran out of IP version 4 addresses. So they said that IPv6 is going to someday replace it. We went from a 32-bit address space. With IP version 4, we had 4 octets, so 4 sets of 8 bits, 32 total bits, to 4 times that, 128 bits with IP version 6. With IP version 6, we have 340 undecillion addresses. And what that essentially equates to, I've heard that there's an IP address for every grain of sand on the earth, which means we're going to have a ton of addresses with IPv6. IPv6 address space is so large that's represented in hexadecimal. So when you look at an IPv6 address, it can be a little daunting because it's in hexadecimal, something we've probably maybe haven't seen before or is relatively new to us. And we went from 32 bits in length to 128. So we're going to refer to each one of these individual sets of numbers as a hextet. Kind of an unofficial term. But this is a hextet, so we have 1, 2, 3, 4, 5, 6, 7, 8 hextets. Each individual number represents 16 bits. So just 2 numbers would be the equivalent to an IP version 4 address. We have a heck of a lot more than 2, right? We have 128. So when we look at these addresses, they can be very large in size. They're hexadecimal. We have a couple different rules in which we can use to shrink them down. The first was omitting leading zeros. It cannot be trailing zeros, otherwise we'll mess things up. So I'll go over this first rule here again real quick. Leading zeros, so we can take 2001, 0 dB8, quad 0, quad 1, quad 0, quad 0, quad 0, 0, 200. And we can shorten that to 2001, dB8, 0, quadruple 1, 0, 0, 0, 200. Note, I cannot get rid of these trailing zeros. I can't just condense that down into 2, because that would completely change that address. Cannot do that. Questions with getting rid of leading zeros? That one should be pretty straightforward and simple. So I'm going to skip to Rule 2. And Rule 2 says that I can take a group of zeros, and only do this one time, a group of zeros, like these 12 zeros here, and I can combine them down into a double colon. So I can take this address up along the top, condense it down to this by getting rid of leading zeros, and taking this group of zeros, replacing it with a double colon. 2001 dB8 0 quad 1 double colon 200. Now a device, a router, switch, a human can look at this number and be able to kind of reverse engineer it, right? I know that there are 1, 2, 3, 4, 5, 6, 7, 8 hextets. And I am only seeing 1, 2, 3, 4, 5. Actually, I'm not going to count that one. I'm only seeing 1, 2, 3, 4, 5 hextets. So I have 8 total typically, but I'm only seeing 5 here. That lets me know, hey, I have 3 hextets of zeros that are being represented by this double colon. So I could expand this out now. 2001, 0, dB8. I'm just showing a 0 here, so that means I got rid of 3 leading zeros. Here comes my quad 1. Now here I hit my double colon. I know this double colon is representing 3 hextets of zeros. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And then my last hextet is 0, 200. Do I have 8 total? 1, 2, 3, 4, 5, 6, 7, 8. I do. I know I expanded it correctly. Okay, keep in mind, I can only use that double colon rule one time. So let me pull up the next example. Which is this right here. So we have 2001, 0 dB8, quad 0, ABCD, quad 0, 0, 100. What I can do is I can take this set of zeros and replace it with a double colon, or, not and, but or replace that set. I cannot do both of them. So I have to pick. And what you typically probably see, and doesn't really matter, but what you typically probably see is you take whatever is going to give you the most amount of zeros, replace that with double colon, or whatever's further to the right, but it does not matter. So there's 2 ways I can compress this. That's down to that, where I'm taking this set of double zeros and replacing it with a double colon. Or I can take this set and replace it with a double colon right there. Okay, the question typically comes up is, well, why can't I do both? Why can't I make it 2001 DB8 double colon ABCD double colon 100. Why can't I do that? Well, the routers, the devices, the switches, us as humans are going to get confused. There's supposed to be 8 total hextets, right? And I'm seeing 1, 2, 3, 4. So I know that I have 4 hextets which are being compressed to the double colons. But does that mean that there's 3 here and 1 here? Or 1 here and 3 here? Or 2 here and 2 here? We don't know that. We can't figure that out. That's why we can only use that rule one time. Because I could have a bunch of potential addresses if I did that. I could have 2001 DB8 quad 0 ABCD quad 0 100. Or I could have went and did 2001 DB8 quad 0 ABCD quad 0 100. I can expand it out the correct way if I do double colons twice. If I do double colons twice. That's why I can only do double colons one time. Let me do another example here. They don't have a good one like I wanted. Well, let's do this one, because this is one we're going to see. So we have FF02 quad 0 quad 0 quad 0 quad 0 quad 0 quad 0 0001. They can condense that all down into FF02 double colon 1. We actually see that number quite a bit. It's a multicast address. So I'll talk about here in a little bit. So FF02 double colon 1. If I gave you that, you should be able to expand it out, right? So let's take a look at what you guys have on that sheet that I gave you yesterday and see if we can figure those two out. So yesterday I gave everybody this sheet here. Did I give you this? Yeah, I give it to you. Okay, we haven't talked about the top two things yet, so that's okay. But let's take a look at this compress. So we want to compress 2001 DB8, 2001 ACAD, 2000, 1000, 0040, 123. Can we compress that down? So what you do is just take it hextet by hextet. So 2001, can I compress that anyway? No, I can't, so that stays the same. 0 DB8. I can take off that 0, so it just becomes DB8. 2001 stays the same. 2000, or excuse me, ACAD. Can't do anything with that. ACAD. ACDC. 2000, can I get rid of these trailing zeros? Nope. I would completely change that address if I did. So that doesn't get changed. 1000. Nope. Trailing zeros, those have to stay. 0040. You take off the 2 leading zeros and make it just 40. And then 1, 2, 3, 4 stays the same. Perfect. Questions on that one? 2001 quad 0 ACAD quad 0 quad 0 quad 0 0001. Let's see how we can compress that. 2001 stays the same. Quad 0 quad 0. I could replace that with double colon, right? Yeah, but
for the triple.
I got this over here. Let's reserve it for that triple. I know I'm really small here, but let's reserve that for that triple so I can get rid of 12 zeros versus 8. So I like your guys' idea there. Let's just make that a 0, right? Let's make that a 0. And let's make that a 0. And then I have ACAD. And now I can use that double colon to try to get rid of all 12 of those. And then 0001 can just become 1. Nice. So there it is, 2001 00 ACAD double colon 1. Okay, let's see if we can do the reverse. I have 2001 Cafe Beef double colon 1. What is that number fully compressed? Well, 2001 and Cafe and Beef aren't going to change, right? But now I run into this double colon. How many sets of zeros is that double colon replacing?
4.
4. I know I have to have 8 total hextets. I have to have 8 total, and I'm only seeing 1, 2, 3, 4. So I know I need 4 more to get me to that total of 8. So it becomes this, 2001, Cafe, Beef, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and then 1 is 0, 0, 0, 1. Do I have 8 total hextets? 1, 2, 3, 4, 5, 6, 7, 8. I sure do. There's that number.
Does that mean someone could have an all beef IPv6 address where it just says beef 8 times?
Yep. My favorite one is feed that beef. Okay, next one. I'm not going to write this out. 2001 0 DAD 00 AC 0200 0001. And then how many sets of zeros is the double colon replacing? Well, I'm showing 1, 2, 3, 4, 5.6. So I'm replacing 2 sets of quad zeros. So it'd be 2001, 0 DAD, 00 AC, 0200, 0001, quad 0, quad 0, 0001. Questions on that? Okay, I want to talk about this here real quick. It's something called the 3-1-4 rule. What the 3-1-4 rule says is the first 3 are our network. The next 1, which I'll circle, denotes the subnet. And the last 4 are for the client. So for every IPv6 number, we actually end up drawing our line right in the middle. And we have a /64, it's known as a prefix length versus a subnet mask. But a /64, we have a /64 for our prefix length for every single IPv6 address. There may be some exceptions to that rule, but that's what I'm going to teach you. Is your first 4 essentially tell us this is the network we're a part of. This is what usually happens. Is let's pretend I'm BSC and I want to run IPv6 on my network. They go to their internet service provider, and the internet service provider says, okay, you can run IPv6. We're going to give you these first 3. You're going to be the 2001 DB8-2000 network, and then you have the ability to tweak that for all of your needs. So what BSC would probably do is they would say, okay, 2001 DB8-2001 0000, you're going to be Jack Science Center. And 2001 DB8-2001 0001, you're going to be the Tech Center. And 2001 DB8-2001 0002, you're going to be the Career Academy. So it gives the businesses the ability to create 65,000 some odd networks. And then once they create that network, everything to the left is that network ID. On each one of those networks, you can have something like, and I'm going to get this number wrong, I should probably look it up, but it is 2 to the 64th power. What is that? Someone plug it in their calculator quick. 2 to the 64th power, that's how many addresses. It's like 17 million devices or addresses you can have on that network. 1.84 million. So Jack Science Center could have 1.84 million addresses on their network, and Tech Center could have 1.84 million, and Jack Science Center and Career Academy, they could all have 1.84 million. That's way more than you'd ever need, right? But that's how they're doing things with IPv6. You get this, first 3, do whatever you want with that, use that for your hosts. So what we typically start to see for addresses is something like this. 2001 DB8 ACAD 0001. Okay, there's my network. First device, :1. Second device, :2. Third device, :3. And actually, if you can start to get a grasp of IPv6 and how to read it and how to write it, it actually becomes much simpler than IPv4 in terms of figuring out your network and usable hosts, and all this different stuff. There's not a whole lot of rules behind it. Okay, I got about 8 minutes, so I want to show you just a little bit more here with IPv6. And I'm going to use Packet Tracer to do it. So if you want to open up Packet Tracer and follow along, you sure can. You don't have to, though.
So is there many things running on IPv6?
There is starting to become more, I would say. One thing that I actually learned the hard way is there are some certain services that do require IPv6 be enabled. And one of those, maybe they've changed it since I ran into this issue, but I was having a heck of a time trying to set up a Microsoft Exchange server one time, and it just would not work, and it would not install, and things wouldn't work properly. And it was because IPv6 was disabled on my computer. It disabled it. Once I enabled IP version 6, it worked great. So there are starting to be a lot of services and devices and websites and whatnot that are using IPv6. And Midco is starting to give out IPv6s to their customers. So if you have Midco and you go onto your router and you view what your address is, you will see an IP version 4 address and an IP version 6 address. So that's great because you can be on the IPv6 internet and network now. And we said that can potentially be much more efficient and quicker. Okay, so the first thing I'm going to do is I'm just going to grab a router and I'm going to pull it up. And I'm going to go to the CLI command here. Now, in order for a router to run IPv6, there's a command you have to type in. And I believe this is on your hands-on final. So you might want to write this down. And that is, you go into config T, and you type in IPv6 Unicast routing, IPv6 Unicast routing. And that basically tells the router, hey, you can run IP version 6 now. Okay? We don't have to do that on a Windows system or a Mac system or an Android phone or an iPhone. It already has IPv6 enabled and running. But for whatever reason, on a Cisco router, you have to enable IPv6 Unicast routing. Okay, as soon as I do that, I'm automatically going to get some IP version 6 addresses on my interfaces. And I should probably look to see what interfaces I have. So I'm going to do a do show IP int brief, just because I want to see what addresses. Okay, so I have a couple of gigabits and a VLAN, but I'm more worried about the gigabits here. So what I'm going to do here is type in do show int. I want to show my interfaces. And actually it's down, so I'm not going to have any addresses on there. So let me go into, I'm going to go into my int gi 0/0, and I'm going to turn it on. Actually, sorry guys, striking out here. It's actually int gi 0/0/0, and I'm going to do a no shut on it and turn it on. So I just basically turn down the interface. And now if I do a show int, I grabbed the wrong router, so I need to do things a little bit more manually here. So I need to do, inside of my interface, I need to do an IPv6 enable. Sorry. Okay. this is what usually happens. This is what I'm trying to show you right here is this right here. As soon as IP version 6 is enabled on an interface, you automatically get an address. It doesn't go out to DHCP to get it. It doesn't have to be manually assigned. It just kind of magically appears, and it's an FE80. You always get an FE80 address. An FE80 address is a link local. That's what's used to communicate within your local network. So all of us in this room are going to have an FE80 address on our Windows machine. And we could use that FE80 address to ping each other to send traffic to. So on your Windows machine, if you go to the command prompt, and you do an ipconfig, either your Ethernet or wireless, whatever you're connected. Here it is, FE80. FE80 double colon A80C colon 1914 colon F713 colon B994. That is my IP version 6 link local address. Someone tell me theirs. Jamie, I know you're looking at it. FE80. 9536. E1F. FD76. 3169. I could take that address and I could ping it, assuming if she's on Wi-Fi and I'm on Wi-Fi. I'm not, though. I'm on Ethernet and she's on Wi-Fi. So by default, you automatically get this FE80. You don't have to do anything to configure it. It's just there. I use that to communicate within the local network. The next address that you would want to assign, and this is something you manually have to assign. This will be the last thing I talk about, so give me just one more minute here. Is what's known as a global unicast. All global unicasts are going to start with 2001. All global unicasts are going to start with a 2001. So whenever you see a 2001, that should tell you that's a global unicast. And what that means is that's the address that I use to get out on the internet. That's my public IP address. And with IP version 6, every address is public if it's a 2001. So two main addresses you're always typically going to see on your interfaces is that FE80, link local, communicating within the local network. 2001, that's a global unicast. I use that to get out of my network. Okay? I know I'm running out of time here and I'm going to stop for today, but if you're interested in IPv6, I highly encourage you to read this section of the book or the curriculum. It really does a good job of going through it. IPv6 is an excellent protocol. It just really hasn't caught on. It can be quicker, can be more efficient, and really, once you learn it, it actually is so much simpler to use. You don't have to do subnetting. You don't have to figure out network addresses and broadcasts and all these different things. There are no broadcasts in IPv6. It's not allowed. There is no broadcast. So the way it works can actually be a big benefit if we ever move towards it. Okay, thank you guys. That's all I got for